Observational studies. There are more airplane deaths now than there were 50 years ago. Does that mean airplane travel is becoming more dangerous? Stop for a second and think about that. No, right? There are a lot more people flying nowadays. 50 years ago, there were not very many people flying, but planes were a lot more dangerous. People who did fly were more likely to die. Nowadays, there are lots and lots and lots more people flying, and so we're going to have more deaths, even though proportionally airplanes are safer now. Right? So the important thing here is not to compare absolute numbers of people, but to compare rates, right? 10 people out of 1 million people flying is less in terms of a rate than 1 person out of 100. So even though 10 times as many people die, there are 10,000 times as many people flying, for instance, in these numbers that I just made up. The death rate in the Navy during the Spanish-American War was 9 out of 1,000. For civilians in the same time period in New York City, it was 16 out of 1,000. Does that mean it's safer to be in the Navy? So here we're comparing rates, right? 9 out of 1,000 to 16 out of 1,000. So we're comparing rates. Does that mean that it was safer to be in the Navy? No, because civilians include people who are old or sick. The Navy, during the Spanish-American War, was comprised of healthy young men. So those people might be more likely to die in combat, but significantly less likely to die from old age or disease or things that kill civilians. So the important thing here, we're still comparing the rates, but we need to make sure that the things that we're comparing are similar. We need to be comparing like to like. Fun example. You may have heard that the theory that COVID-19 is caused by 5G towers. And when we look at this, here's a map of COVID-19 cases, and here's a map of 5G coverage. And they look kind of similar, right? You can see you've got some hotspots here. You've got a whole bunch of COVID and a whole bunch of 5G here. You've got this spot in Colorado, right? Spot here in California. So where we have more COVID-19 cases, clearly we have more 5G coverage. So is there a correlation between 5G and COVID-19? Yes, there's a correlation, right? We see that in places where we have more 5G, we have more COVID-19. Can we determine that 5G causes COVID-19? No. Just because two things happen together does not mean that one thing causes the other. So this is a very important rule, that correlation does not imply causation. Just because two things happen at the same time does not mean that one thing causes the other. And so when we're looking at a correlation, it's important to consider the confounding factors. So other things that could be causing this relationship that we're seeing. In this case, if you look at both of these maps, they are remarkably similar to a U.S. population density map. Places where we have more people, the little spot in Colorado, the Pacific Northwest, California, places where we have more people are places where we have more 5G coverage, and also places where we have more COVID-19. So population density is a confounding factor. In a 1975 study of 1,314 British women, they did a follow-up 20 years later and found that 24% of smokers had died by the 20-year follow-up, and 31% of non-smokers died by the 20-year follow-up. Does this mean that smoking makes people live longer? Right? There was a greater percentage of non-smokers than smokers that died over the course of the 20 years. So does this indicate that smokers live longer? When we look at the data here, we see that among the smokers and the non-smokers, both groups had about the same amount of people who were aged 18 to 64. But among the smokers, those people aged 18 to 64 were more likely to die if they were smokers. 18% of those aged 18 to 64 of the smokers died, and only 12% of the non-smokers died. In the age 65 and up category, there were only 49 smokers who were 65 plus. There were over 3 times as many non-smokers who were 65 plus. And so those two groups in the age 65 plus, they had pretty comparable death rates. But because there were so many more non-smokers who were older, that means that the total number of non-smokers who died ends up being greater than the total number of smokers who died. Right? 18% of 533, 96 of the smokers died in the 18 to 64 category, compared to 65 smokers who died in the non-smoker category, in the 18 to 65 category. But of the 65 and up, 42 of those 49 people died, and 140 of the 165 people died. So when you total these up, you end up with a greater percentage of non-smokers who died, but that's because you had more old people. So, do smokers tend to live longer? No, age is a confounding factor. In the younger people, the smokers were more likely to die. In the older people, the smokers were still more likely to die, but basically about the same rate. So, age is a confounding factor. So, a confounding factor, the definition that you need to write down in your notes, is a confounding factor is a variable associated with both the explanatory and the response variable. Because of this, the response could be due to the supposed explanatory variable or to the confounding factor. The two are confounded. In the previous example, the supposed explanatory variable was smoking, and the response variable was the death rate. But the confounding factor is age. There were more older people in the non-smoking group, and older people are more likely to pass away within 20 years. So it could be that smoking did affect whether people died within 20 years, but it could also be that it was as a result of their age. Let's say you have a hypothesis that prolonged smoking leads to dental problems. How would you collect data to test this hypothesis? Should we do an experiment? Can we have two groups of people and assign one group to smoke and one group to not smoke and see how compare the rates of dental issues? No, we can't do that. It's unethical. We know that smoking is harmful. Even if we don't know that it causes dental problems, we know that it causes a variety of other health problems. And so it would be unethical to assign people to smoke. We can survey people and ask about smoking habits and dental health. And this may show a correlation between smoking habits and dental health, but it will not prove a causal relationship. Observational studies can never prove causation. Only experiments can prove causation. In an observational study, you have lots of possible confounding factors. Again, we saw that age is one. That study was from 1975 to 1995 when smoking was becoming popular. Now it's becoming less popular. So nowadays, maybe more older people smoke rather than younger people. Older people also likely have more dental problems. Income level is also a confounding factor. Poor people are more likely to smoke and more likely to have dental problems. Things like stress levels, things like diet, all of those things can be confounding factors. So, the best thing that we can do is an observational study and try to compare like to like. Older people to older people, women to women, people of the same income levels, etc. And we'll talk more later on in the course about how we go about controlling for these different variables, these possible confounding factors. So, important takeaway here, observational studies alone cannot prove causation. Absolutely cannot. Only well-designed experiments can prove causation. Observational studies can indicate correlation, but they cannot prove causation. Super, super, super duper important. Observational studies can make generalizations based on samples that are representative of the population. We'll talk more about sampling methods in a later video. But you can generalize from the sample to the population if the sample is representative of the population. Experiments generally cannot do that. A sample is only generalizable to the population from which it is selected. So if I take a random sample of capstone students, I can only generalize my results to capstone students. I cannot make generalizations about all high schoolers, or all people in the city of Atlanta, or all Americans. And, some fun little jokes. I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy. And a graph showing that as the number of out-of-hospital deliveries increased, so do the number of pairs of storks. So clearly it must be that storks are delivering babies.